All right, there's nothing like starting off a lecture with a hidden word. So why don't we start off with bad penny? B-A-D-P-E-N-N-Y, bad penny. The green arrow villain, bad penny. What we're exploring in this lecture and the next one after that, are ways to use information gathered from experimental results that's been compiled in tables to calculate unknowns. In other words, we're using some mathematical tools that will let us easily calculate enthalpy. These all fall under the category of Hess's law. Before we talk about Hess's law, we have to garner some tools to use while working with chemical reactions. The first of these tools is the fact that when you multiply a chemical equation by a number, you multiply the change in enthalpy by that number. So, to start with, I have this generic chemical reaction of aluminum reacting with iron 3 oxide to yield iron and aluminum oxide. And it has a change in enthalpy of negative 852 kilojoules. Let's say I wanted to multiply all the coefficients, and by coefficients, remember, I mean the numbers out in front of the molecules here. Let's say I want to multiply those numbers by 3.5. Well, if I multiply all those coefficients by 3.5, I'm also going to multiply the change in enthalpy by 3.5. So 2 times 3.5 is 7. 1 times 3.5 is 3.5. 2 times 3.5 is 7. 1 times 3.5 is 3.5. So I have my new equation. And the change in enthalpy for this equation is 3 times our initial change in enthalpy, or a negative 2,980 kilojoules. Translation, you multiply the coefficients in a chemical equation by a number, you have to multiply the change in enthalpy by a number. What about division? Same thing holds. I had a math professor who would argue all the time that there is no such operation as division. No. There's no such operation as division. You're simply multiplying by the multiplicative inverse of the number. So, in other words, the rule also holds for division. So if we were to cross that out and say division, I guess I should say divide. Whoa, really sloppy with the stylus today. So when you divide a chemical equation by a number, you divide the change in enthalpy by that number. So it works for division as well. Another great tool, when you reverse a chemical equation, you change the sign of the equation. For example, I have that reaction we were looking at last time, and it's an exothermic reaction. If we take this reaction and we reverse it, in other words, we run it backwards, my products are now my reactants, and my reactants are now my products. If I reverse the chemical equation, then I change the sign of my change in enthalpy. And this really makes sense, right? If it's an exothermic reaction going forward, it makes sense that it would be an endothermic reaction flowing backwards. It's really easy to see the basis for this rule if we look at it in terms of how a biochemist would view this equation, right? If it's an exothermic equation where heat's being given off, a biochemist would write the equation this way, with energy as a product, so it just makes sense that if we were reversing the reaction, then when a biochemist write it, we'd see it as a reactant, which means it would have a positive change in enthalpy. I think it's a little bit easier to see the basis for this rule. Bottom line, when you reverse a chemical equation, you change the sign of enthalpy. You also write down black arrow. Why don't you write down black arrow? I hope you're writing down black arrow. With these mathematical tools in mind, we are now able to address Hess's law. Hess's law. It sounds like a really bad cop procedural. Tonight on Hess's Law, we mercifully track down the enthalpy killer. They take different body parts and they sew them together, which is surprisingly an apt description of what Hess's Law does. Hess's Law says you can take two equations, you can take them apart and sew them back together to form a third equation and add the enthalpies of the two bodies or equations that you slew to get the equation of the third. And now I'm going to stop talking like this because it's really hurting my throat. Hess's law states that the overall enthalpy change for a reaction is equal to the sum of the enthalpy changes for the individual steps in the reaction. What that means is, if I want to determine the enthalpy change for the reaction of 3 moles of hydrogen with 1 mole of nitrogen to yield 2 moles of ammonia, I don't have to be able to measure the change in enthalpy for that reaction directly if I can measure the enthalpy of the steps that makes up that equation. For example, the Haber process, which is the reaction of hydrogen and nitrogen to yield ammonia, doesn't take place in one step. What actually happens during the reaction is 2 moles of hydrogen react with 1 mole of nitrogen to yield what's known as an intermediate. When we measure the change in enthalpy for this first reaction, we discover that it is endothermic with a change of an enthalpy of 95.4 kilojoules. Well, this reaction intermediate then goes on and reacts with hydrogen to form our ammonia. The change in enthalpy for this step is a negative 187.6 kilojoules. If I look at these two subreactions here, I can see that when I add them together, I get my third reaction. I'm going to label my reactions 1, 2, and 3 here. When I add my two reactions, what happens? First of all, when you add equations in chemistry, you can treat them just like you would adding two equations in algebra class. Meaning that if something's on opposite sides of the equal sign, you can cross it off. Notice that I have this compound as a product over here and as a reactant over here. So they're on opposite sides of the equal sign. That means I can cross them out. Then, if I look at things, I have 2 moles of hydrogen here, 1 mole of hydrogen here. 1 plus 2 is 3, so I have 3 moles of hydrogen. I have 1 mole of nitrogen, and then I'm left with 2 moles of ammonia. So I can add these two reactions together to get a third reaction. Whenever I can do that, that means I can add their enthalpies together to get the enthalpy of my third reaction. So if I add the enthalpy, the change in enthalpy of reaction 1 plus the change in enthalpy of reaction 2, I get the change in enthalpy of reaction 3. And if we check and verify our theorem here, 95.4 plus a negative 187.6 does in fact equal a negative 92.2 kilojoules. Let's take a look at some more examples here. Alright, this is a typical type of Hess's law problem or Hess's law situation. You have an equation right here that you want to know the change in enthalpy for. You don't know its change in enthalpy. You do, however, know the change in enthalpy for two other equations, and your task is to combine these two equations in such a way that they add together to get the third. In order to add them together to get the third, you can do whatever it takes. You can multiply them by a number, you can reverse them, you can switch them, you can do whatever. There's a sort of order to the process that I think makes it a little bit easier. The first thing I like to do is see So the first thing I like to do is I like to see is, do I have products or reactants on the right side? By that, I mean I have propane as a reactant in the equation I'm wanting. In one of the two equations I've been given, do I have propane as a reactant? Hey, yeah, I do. Okay. I have water as a reactant. Do I have water as a reactant in one of my problems? Hey, yeah, I do. Matter of fact, I've got it in two problems. Next, I've got carbon dioxide as a product. Do I have carbon dioxide as a product in one of my subreactions? Oh, hey, yeah, I do. Then I see, do I have hydrogen? I have hydrogen as a product. Do I have hydrogen as a product down here? Yeah, I've got it as a product in two equations. Okay. So once I'm sure that I have my products and reactants on the correct side, I begin to look at those. All right, so I don't have to reverse any equations. So I can check that off. Check. So I can check that question off. The next thing I need to do is I need to check numbers. In my first equation, I have one thing of propane. I have one thing of propane down here. Now I have 6 things of water here, but down here I have 3 plus 1 is 4. So down here I only have 4 things of water. So I'm going to have to change one of these two equations in order to bring my total waters up to 6. So what equation should I change in order to get 6 waters? Well, you can't just multiply water by something. You'd have to multiply the whole equation by it. If I multiply my top equation by a number, I would change not only my number of waters, but I'd change my quantity of propane. Well, I'm happy with my quantity of propane. I don't want to change it. So I want to keep my hands off that top equation if I can, which means I'm going to want to multiply my bottom equation by something. I want a total of 6 hydrogen. I want a total of 6 waters. I have 3 from this equation, so I need to get 3 out of that equation. Here, for easy convenience sake, we'll call this equation 1, that equation 2. I want a total of 6 I want a total of 6 waters. I have 3 waters from equation 1. How many waters, therefore, do I need from equation 2? I need 3 more. Therefore, I'm going to have to multiply equation 2 by 3. When I do that, I get 3 carbon monoxides. I get 3 waters. I get 3 carbon dioxide gases, and I get 3 hydrogen gases, and my change in enthalpy becomes a negative 41 times 3, or negative 123 kilojoules. Writing with the stylus is harder than one would think. Okay. All right, so now let's see if we can focus this a little bit. Alright, so we multiplied our second equation by 3, and that solved our number of water problem because we now have a total of 6 waters. Our number of propanes is correct because we haven't changed them. Our number of carbon dioxides is correct. We have 3, and we don't have carbon dioxide anywhere else. How about our number of hydrogens? We need 10. Do we have 10 here? I've got 3 here, 7 there, it's 10. Then I have one other concern. I have carbon monoxide. Does carbon monoxide appear in my overall equation? No. So it should be canceling out when we add together. I've got carbon monoxide here, carbon monoxide there. Hey, 3, 3, so it'll look like they'll cancel out. So what I'm going to do now is I'm going to add my equations together. And in case you're wondering what happened is I took this equation down there and to make things look easier, I rewrote it right here. Yes, just copied that equation verbatim right there. Alright, so now I'm going to add my 2 equations together. I have carbon monoxide on one side of the arrow. I can cancel it out with carbon monoxide on the other since my number of moles are equal. So then I have C3H8 on my propane. Then I have 3 plus 3 or 6 waters. I have 3 carbon dioxides from my top equation. I have 3 plus 7 or 10 hydrogens from my bottom equation. So my equations match. So I've done everything correctly. So now all I need to do is I need to add my enthalpies together. So the change in enthalpy for this equation is going to equal 499 kilojoules plus a negative 123 kilojoules, and that's going to give me a positive 376 kilojoules for the change in enthalpy. And that's how you do a Hess's law. Write down count vertigo. Write down count vertigo. Not only a green arrow villain, but a member of the Suicide Squad. Count vertigo. Write down count vertigo. COUNTVERTIGO. Count vertigo. Then proceed to the light scribe for some more examples on Hess's law.